line. This is our stress Y line. This is our shear XY line or shear YX, either one. Okay. Okay, now this is where things get a little bit confusing. Okay. What do I mean by that? Where is point X and where is point Y on Mohr circle? Okay, so I want you to just listen. Okay. So we know that point X will lie on either the top part or the bottom part that I highlight in yellow. So is it the top or the bottom? It depends on the element rotation due to the shear. Okay, what do I mean? So now we put our finger on the center. Okay, we are going to do X. Okay, put our finger in the center. We're going to pin it. If we look at this yellow shear, the 20, it's going to generate a rotation of the element in what direction? The clockwise direction. So this is our point X. Okay. I will do again for our point Y. Okay, I will do again for our point Y. So the Y, right, will be either at the top or at the bottom. Okay. So if we were to focus on our Y, if you look at this blue highlight arrow they have just done, it's going to induce a rotation about the pin, okay, about center in the clockwise rotation. So this is our Y. Why I say it's confusing, in normal stress, right, anything towards the right-hand side is tensile. So anything positive is the right-hand side. Anything negative is on the left-hand side. It's in compression. So the normal stress, the sign does mean something, right? For the shear, it means nothing. Whether is it positive shear or negative shear, it means absolutely what? Nothing. Okay. So why do I mean by that? Because if you look at over here, we have what? We call this shear configuration as positive 20, right? But in fact, if you look at point X, okay, so if we look at point X over here now, if we look at point X, right, the shear is going to generate an element rotation of what? Anti-clockwise. So this corresponds to element rotation anti-clockwise. That's why X is down here. Okay. And if you look at Y, right, look at Y, right, it's going to rotate. It's going the rotate is going to induce by this shear, and the element will rotate by what direction? By clockwise. So clockwise, Y is on top. Okay. So that's where the confusing part. So positive shear, negative shear means nothing on Mohr circle. It all is dictated by the rotation of the element. Okay. So from here, we can do some very basic calculations. So the first thing we're going to do is draw a line from here to here. We'll join them. And where it intersects the zero line, the zero shear line, I'm going to draw a green line now. Okay. And this corresponds to our average shear stress. Okay. So the average stress, or the center of the circle, O, I call this O, yeah? The center of the circle correspond to our stress average is equal to stress X plus by stress Y divided by 2, right? So this will give us, this will be equal to 30 plus 10 divided by 2 will give us 20 megapascal. Okay, so that is our stress average. Now, another thing to take note is the angle between X and Y. Okay, between X and Y, right? Between X to Y. So X to Y, the angle over here, the angle over here is, what angle is this? 180 degrees, right? On the element, okay, on the element, it is what? From X to Y, what is this angle over here? 90 what? Degrees. Okay, I repeat again. On the Mohr circle, the point X and point Y is 180 degrees. On the element, it is 90 degrees. Okay, now some of you will be babbling. Why are we looking at element and why are we looking at Mohr circle? Okay, the element, it is the what? It is the real world. It is where we are. We are in the element world. Yes or no? Right? The Mohr circle is an analysis tool. Are we clear? Okay, so you have to relate what is going on to the real world, to the Mohr circle, and then from Mohr circle back to the real world. I'll give you another example that you have seen it before. Have you guys done Laplace transform yet? Yes or no? Yes, Laplace, okay? You have time domain, which is our domain. Then we have what domain? S domain. What is S domain? Any idea? Why do you learn Laplace transform? Anyone? Holy shit, this does not look good, man. Right? The only way to divide two second order differential equation, you cannot do it in what? Time domain. But you can do it in what? S domain. That's it. That's why you learn Laplace. That's the only reason. Okay? I mean, to me. Okay? Right. Coming back to here now. So I'll write this out. So in Mohr circle or in element domain, is theta. Okay. In Mohr circle domain is 2 theta. Okay. I don't want to prove to you mathematically because we'll write 2 pages of formulas and equation. I rather relate this way to you all. Okay. So this is another important thing to know. So I'll write here, this is theta, right? And then over here is 2 theta. Okay. Oh, this circle look like kind of a mess. Okay, I'll let you guys copy some more. Okay. Okay, so now I need more space, so I'm going to copy this thing and I'm going to, bear with me, okay? Copy, and usually it will not work, okay? It will crap out somehow, I don't know why, Microsoft. Or the user, I think it's a user. Oh, perfect. Not really, but close enough. Okay, okay. Right, so we just talked about the angles. So next, we are going to draw the circle. Okay, so sorry, next we are going to find, let me zoom out. We are going to find radius of circle, radius of circle. which correspond to your tau max. Okay, which correspond to your tau max. So the radius of the circle is equal to (10^²), okay, plus by 20^². And you square root the whole thing. So the radius of the circle is equal to 10^² plus by 20^², square root the whole thing is equal to 22.36. Okay, so how do we get 10? Okay, so the distance, so what we want to find is the distance from here to here, or the geometry from here to here. This is your radius, right? So we know that the distance from here to here is 10, and the distance from here to here is 20. Okay, very simple math. So from here, you can find your principal stress. Which is your stress 1 and stress 2. So the principal stresses are equal to the stress average plus minus by a tau max. Okay, so this will be equal to your stress average is 20 plus minus 22.36. So this will be equal to 42.36 megapascal or minus 2.36 megapascal. Okay. So where are they on our, so 42.36. So this is your stress 1, and over here, this is your stress 2. Okay. So from here, we can construct a circle. This is just eyeballing, okay? Okay. So this is your, yeah, the eyeball is not very eyeballing, is it? Okay, okay. So this is your Mohr circle. Now this circle belongs to the XY plane. And the XY plane is also known as your in plane. Okay, it belongs to the XY plane, is also equal to your in plane. So this surface over here is your what? XY what? Plane, and is the biggest surface that you have on the element. Okay. Or is the only surface you can see in 2D. Okay. Now, question asked is why this is stress 1 and why this is stress 2. It can flip over, does not matter. Okay, so you realize that in the principal stress, okay, at the principal stress, right, the shear stress is equal to what? 0. Right? At the principal stress, the shear stress is equal to 0. So now we are going to calculate the principal plane. Okay, principal plane. And the principal plane, what we are trying to determine down here is from X to the 0 shear stress line. This is known as our 2 theta P. Okay, you can do it from Y also, is the same thing. Okay, it's still the same rotation. It's going to rotate anti-clockwise. and this angle is also equal to 2 theta p. Okay, so now we can find, I will zoom out, okay, tangent to theta p will be equal, can you all see? You all can still see, right? Okay, tangent to theta p is equal to 20 divided by 10. Okay, so 20 divided by 10. So theta p is equal to, or 2 theta p is equal to 20 divided by 10. Inverse tangent is equal to 63.4 degrees. Now in degrees, 1 decimal place is enough. Yeah, don't give me 3 decimal place. I can't draw that. And then theta p is 31.7. And both are going in the anti-clockwise direction, because this direction, right, this direction over here is anti-clockwise.